first of all, thanks everyone for being here. Thank you guys for putting on the event, SEDS. It's always awesome to be here. My name is Owen Marr. I'm the program manager for Blue, and I'll get into it, but that's one of the project teams under SEDS. And so over the next 10 or 15 minutes, the goal is just explain the Blue program, let everyone know the work that our students have been working on over the past year, and talk about the launches we have coming up, because we have 3 payloads launching this year, which is really exciting. So with that, we'll get into it. I think I already explained the agenda basically, but we'll talk through the 3 payloads briefly, talk about the launches, and just kind of explain what we do, because it's a fairly unique way to build spacecraft. So for starters, University of Michigan, we have a SEDS chapter. Blue is one of the project teams under that. So that's what we're talking about today. And it looks like my animations are messed up, but there are 4 payloads that Blue has done to date. And so we're going to talk about 3 of them. And it's going to be the 3 that are launching later this year on 2 different rockets. So we'll get into it. As I said, 3 of them are launching. So BX2 and BX3 are both launching with Blue Origin in Q3. As we get closer to the launch date, we'll be able to publish when exactly it's going to be, but we're very excited to have those launching with Blue Origin. And then BX4, who, if you were at the last talk, Liam is one of the team members from there. There's a team that's working on this one, which will be launching in December of 2021 on the MASA rocket. So if you were around earlier today and you heard about MASA's super awesome rocket, they're going to space. It's going to be the first student-built liquid rocket. This is the payload for that rocket. So we'll start with BX2 and BX3, which are sister payloads. They are both 2U. They both go up on Blue Origin's new Shepard rocket. So basically they take the seats out from where people would sit. And if anyone hasn't seen, Blue Origin just announced July 20th will be the first time that this rocket launches people. And then we will be the next launch after that. But so what happens is they tear all the seats out and they put these payload bays in. And so we purchased 2 of these 2U spots, and that is BX2 and BX3. These payloads are developed by students. And so it's really awesome. It's usually a team of 10 up to 20 students that are working on it over the course of a full year. With COVID, our schedules got a little mixed around, but we were still able to get the payloads done. And it's sweet because it's student-led spacecraft development. There's a professor that oversees stuff, but it's really led by the students, and there's no research group associated with it. It's whatever the students want to do. And so this one, we do have to get it passed by a board of professors. And so this one, BX2, is all about demonstrating the use of ultrasonic transducers to manipulate bubbles that are inside a tube of water in microgravity. So the use cases here are for removing gas bubbles from fuel tanks. You really don't want to push bubbles through an engine. And so if you're starting up a rocket that's in orbit, that's in microgravity, that's one of the use cases. And then also if you want to do electrolysis, a lot of lunar and Martian bases use electrolysis to generate oxygen. And a lot of deep space missions want to do this as well if we're sending humans there. And so being able to separate the gas without having to, by using these ultrasonic transducers is going to be pretty important. So what are we doing here? We're generating a gas bubble. We're using the transducers and taking a video to show that we can manipulate the bubble. Here's what the payload looks like. The majority of the payload is just this bay of liquid water down here. And then all our avionics are stored up top. It's 2U, so it's about the size of a tissue box. And then it's wrapped in carbon fiber as the outer shell. Here's some photos of the team, although mostly just hardware because a lot of the manufacturing was done during COVID where it was just 1 or 2 of us in the lab. But you can see some of the PCBs. We have students that do carbon fiber layups. This third picture here is on the bottom. There's some 3D printed parts that are carbon fiber reinforced. And then a lot of this stuff is water jet carbon fiber. So it was a good way for students to learn how to use those different machines. On the right there, you can see some of the sub-assemblies for the payload. And then finally on the left image here, you can see the completed BX2 payload. There's a structural mock-up on the right there that shows what it looks like on the inside, but from the outside, it just looks like a black box. And then on the right there, you can see our vibration test. Spurl at the University of Michigan was very kind to lend us time on the table so we could do a vibration test. And that's just where you shake it to make sure that it's going to be able to work after it goes up on the rocket. So that's BX2. BX3 is, as I said, the sister payload, and this one is curing composites in space. And so it's based on some other research that was done by a university in Greece. And they did it on microgravity parabolic flights. We're doing it on a longer duration microgravity, but we're going to be curing a composite in space, curing an identical composite on the ground, and then strength testing them to see if the microgravity cured one is any stronger Theoretically, the wettability of the fibers is better in microgravity, so we're hoping it's going to be a little bit stronger. This would be a huge kind of proof of concept for doing in-space manufacturing and in-orbit manufacturing. And so you can see on the right kind of the different components to the payload. There's nothing moving. It's just the lights turn on and cure the composite, and then it comes back down. So it's perfect for a suborbital flight like this. And then what they're going to do, a lot of the work is when they bring it back down, they're going to follow this testing standard that's pretty standard from material science. So they're going to cut the piece up into strips. They're going to do tensile strength tests. They're going to use some special imagery to look at what happens and if they break differently when they do fail. And then they will be publishing those results. And hopefully we'll make some composites that are slightly stronger than Earth-based composites, which would be really cool. So those are the two that are launching in August. And then the third payload that's launching this year is BX4. This is a little bit larger of a payload. It had a bigger team. It was run as a senior design class. And so now we're going to talk about this one in a little more detail. If you were at NASA's presentation earlier today, you saw this. They're building a really cool rocket. It's super impressive that a university is able to build something that makes a person look so small in the bottom right corner there. But yeah, they're competing for $1 million prize if they're able to pull it off. And so we thought it would be really cool because it is such a monumental launch, the first student-built liquid rocket, if there was a way to take pictures of it. And so we actually approached NASA and said, like, hey, do you have enough mass to spare that we could build something that deploys out of your rocket? And so they messed with their budgets a little bit and gave us a couple kilograms. And so the BX4 payload sits in this rocket. And what it's going to do is, I'm going to skip ahead one slide. It's going to go up with the rocket. It's going to deploy above the Kármán line. That's kind of what's the edge of space. And then it's going to turn around and take pictures of the rocket, take pictures of the Earth towards Ann Arbor, and then it's actually going to come back down and deploy a parachute. So it's the size of a CubeSat, but it's going to come back and it has a parachute attached, which is kind of the key difference between a normal satellite. This will all be happening down in December at Spaceport America, which is out in the middle of the desert, and then it actually lands in the White Sands Missile Range. So I'm going to go back one slide and show you kind of what the payload looks like. So on the left here, you can see where it fits. It fits in between the helium tank and the avionics, which is like the computers that run the rocket. And on the right here, you can kind of see what it looks like. It's a unique shape because it's actually built into the side of the rocket, which is why it's curved. But we have a couple of video cameras on there, an imaging camera. One thing that's really cool is we have a reaction wheel system, so we can orient the payload and point in specific directions. We have a flight computer and some other electronics. And then this yellow circle here, you can't really see it because it's mounted to the underside of the payload, but that's where the parachute is. And so I'll just kind of jog through these subsystems really briefly so everyone can see what they're about. And then we'll talk about the launches at the end. So as I said, the whole purpose of this is to take images and video of what's going on during the launch. And so we have two 4K cameras that'll be pointing in opposite directions. We have almost a 360 field of view. And then we have an imaging camera that's an 8 megapixel sensor that'll be fixed. And that actually is going to lead into some computer vision stuff that I'll talk about in a second. But that's how we also point the payload and point towards the rocket. So it's pretty cool. We've been able to use a lot of commercial parts, mostly from drones. So these are the smallest or lightest 4K cameras on market right now. They're actually meant for drone racing, but it's really great because they're already built to withstand vibrations and accelerations. And so we're able to flight qualify all these components by running them through a thermal chamber and a vacuum chamber, which simulates space conditions. And so all of our electronics have already been through this process. The attitude determination and control system, again, we'll be getting data in just through an IMU, and then we'll have an algorithm running on our flight computer that will spin these wheels up and down so that we can control the orientation of the payload. And this is a pretty standard thing to have in a spacecraft, but we have to do it really quick because we only have a couple minutes. We're in space. So it's really important that this works pretty quickly. So that's one of the big challenges with this payload. So some other things, I talked about the picture on either side here, but this middle one shows a little bit of what our computer vision is doing. And I'm actually just going to go to the next slide, but we're running a computer vision algorithm that will be able to detect the rocket it takes pictures, it blurs them, and then it runs an open source algorithm to kind of turn it into these little shapes you see down here in the bottom right. And then from there, it can tell the control system where the rocket is, and it'll kind of tell exactly which way we need to point so that we're focused center on the rocket. And so that's one of the really interesting computer science problems that's been worked on this year. Here you can see the electronics, not too much to mention. Just you can kind of see how everything's laid out. There's one motor for each direction so that we have 3-axis stabilization. Our power bus kind of sends all the right amount of power to everything. And then, yeah, the camera's wired right into the board, and the video camera is just directly powered. It starts as soon as it is provided power. So that's how everything's laid out. Our structures team is also doing some pretty unique work. So the cool thing is the entire bus, which is like the main structure, is 3D printed. And it's 3D printed with a material that's been on a CubeSat before. So it's been space qualified. But it means we can get really creative with our shape. And we can also build a lot of the component mountings right into the structure. And I know that might not sound interesting if you're not a structures engineer, but it's a great way to save mass and reduce complexity. So that's one of the cool things we're working on. There is an aluminum plate on the front because, as I'll show later, it's built into the side of the rocket, so it needs to withstand the thermal loads going up. And as I said, in the very bottom right here, you can kind of see there's mesh that goes over the parachute housing, and that parachute housing is the same piece as the satellite bus again, because we're able to 3D print this and get really unique geometries. So here you can see an FEA simulation. This is exaggerated deflection, but just wanted to show that a lot of the Mechie students have been working on a lot of good simulations to make sure that we can withstand, especially since it's a plastics-based 3D printing that we're doing. Just making sure that we can withstand the flight loads is really important. And so there's been a lot of good engineering tools being used by the undergrads as they go through this. Here you can kind of see again how it's oriented and how it deploys. We're actually using this black cylinder is usually meant to deploy stages of model rockets, but we've just mounted it sideways, and that's how we deploy our payload. So again, using commercial off-the-shelf parts for a lot of this. But this is how it deploys, and you can see like there will be a hole in the rocket once it deploys, but NASA is not really concerned about the orientation as it comes back to Earth, so that's all right. As far as actually recovering everything, we have a parachute that's going to deploy. It's deployed by cutting some wires using this picture here in the middle. So what will happen is this sensor has a barometer in it. Once we get to a fixed altitude, it'll signal this will cut the wires, and then that'll allow the parachute to deploy. So a lot of testing going on right now in the wind tunnel to make sure that the parachute deploys correctly. Again, that's kind of one of the cool things about this is it has a parachute, but it's a satellite. It's kind of a weird mixture, but it's part of what makes it exciting to design. So here you can see a cutaway. I separated it from the main part of the bus so you could see it, but like I said, it's printed right into the main part of the structure. But this is how these mesh panels kind of just open up, and then the drag will pull the parachute out on its own. So hopefully going through all the subsystems, that gave you a better idea of what this whole ConOps is going to look like. We're really excited to do this. This is the first payload we're building that's going to actually go outside the rocket, because all the other ones with Blue Origin, they stay in the crew capsule the whole time. And so we're excited to be a part of NASA's really cool journey, quite literally going up, taking the pictures, and having some really, really cool images and video to show, and kind of just show off what the university and its students are capable of, which will be really cool. As far as the timeline, this is the main thing that we're working on over the summer is designing or finishing up the design. It's almost frozen at this point, but doing a lot of the manufacturing and testing. So we have a ton of summer plans. I'll be working on it. We have a team of 13 students. So it's myself and one other grad student kind of leading it. And we have 11 undergrads from a bunch of different majors, which is awesome. We're going to be manufacturing, assembling, testing, including all the code. Then we'll go through that same vibration process in the fall where we test it out and integrate it into the rocket. And then, yeah, like I said, launch is in December. So we're really excited to have, it looks like BX3's image didn't show up here, but we're really excited to have 3 different payloads launching this year. Students have been working on this for a number of years now, so it's exciting to see all these things coming up. We're, really grateful to everyone that supported the program, the university, and all the funding, and also like the lawyers that it takes to get all the contracts signed is really undervalued sometimes. So huge thanks to everyone that's helped out with the program. We're really excited to kind of finish these things up over the summer and get them launched in the fall. So I will wrap it up there. And if there are any questions, feel free to ask them now. If you're interested in joining the team or you just want to email a question, feel free to send me an email as well.
That was fantastic. Thank you, Owen. It was really good. I haven't heard most of that about BX4, so that was really cool to be able to see all the work that has been put in, even during the pandemic. So
yeah, It's difficult to get into the labs, but the university's been pretty accommodating of letting us go in. And yeah, we have been pretty quiet about it because it's been happening slowly but surely over the course of the year. So
Mhm.
we're excited to get stuff going in the summer again. We've taken a week off and we're ready to get back on Monday.
Yeah.
Right.
Yep. Busy stuff.
Mm-hmm. And I mean, you've been here since the beginning of Blue, and you kind of see the journey over the last few years. So what do you envision for the future of student developed spacecraft?
Yeah. I can't talk about everything, but I can say there is going to be like the first official CubeSat class is going to be this fall. If you are interested in that, you can email Professor Cutler. He's the one putting it together. Um, his lab has traditionally done research and it's been a lot of graduate students, but we've gotten enough experience and like a lot of the technology is becoming so standardized that we can drop it down to the undergrad level. So that's definitely something. If you're a student and you want to work on spacecraft, come the fall, there is going to be a CubeSat class. And so you can email Professor Cutler about it if you're really interested. And he'll be able to announce more information as we get closer. But that is one of the really exciting things coming up.
Yeah, I think it's really impressive that you're going to have 3 whole payloads being sent this year. I'm sure
Yeah.
there's been a lot of work with coordinating and stuff. And again, sort of ties back to the space law from earlier, getting that all to work out. So, yeah.
Yep. Yeah. 2 of them should have launched last year, but then with COVID, the launch got canceled. And so it kind of just ended up that all of them are going to be launching within 5 months of each other ish. And so, yeah, BX2 is sitting in clean storage. BX3 is still getting finished up, but yeah, those are pretty much ready to go. And BX4 will be done over the summer in terms of fabrication. So it'll be cool to see them all launch.
Yeah, looking forward to it. And congrats to the whole team. It's a lot of effort.
Yeah, it is. We've had really good students this past year.
Well, if anybody has any questions, feel free as always to send them in the chat. Otherwise, you can send them in the Ask Anything channel in Slack or email Owen. We have quite a bit of time.
Yeah, that's okay. We can cut to break, but I do have, I actually have one question, Owen. Could you elaborate a little bit on what the brainstorming process is? I know some of the payloads are based off of previous research, but, how does the team decide what they're going to spend, 6 months of the year working on?
Yeah, that's a great question because it is like only one idea that can be selected. And so it's usually, I think the first assignment when we run it as a senior design course is like everyone comes up with an idea and then we do voting. So everyone will present for 5 minutes. We'll down select to about 2 or 3 ideas, and then they'll go split up for a week in small teams and kind of put together a more formal presentation. And then again, it'll be voting of those final ideas. And so we like to make it a competitive process so that the best ideas come out on top. And so, yeah, a lot of times it does have to do with other stuff that's going on. But sometimes it's just like an idea that we think has good applications for space. And obviously with the massive one, we knew what we wanted to do going in because we were just like, it'd be really cool if we could capture video for this awesome launch that's going on.
Yeah, thanks.
Okay, so our next talk isn't for a bit. I think it's at what time?
4:15.
4:15. So we've got about 30 minutes almost. A little less than 30 minutes,
Quick
I think.
math.
Quick math. So feel free to like take a break, stretch again, get your eyes off of the screen for a while, and then we'll reconvene with Alex from Maxar.
Thank you guys.